Today we're going to look at projectile motion, and first we're going to look at projectiles launched horizontally. Now, first of all, a projectile is an object that is initially projected by a force, but what happens is once the force lets go, the force is no longer acting on it. So let's say I had a ball like this, and let's say I was pushing it through the air. Once I let go and I'm no longer pushing it, the only thing that's acting on this ball as it's moving is gravity. So gravity's pulling it down. So the force you apply when you throw it makes it go forward at a constant speed, but the only force acting on it, again, is the gravity that's pulling it down. And because of this, we're going to see that because there's no horizontal force, there's never going to be a horizontal acceleration. Now, this is the picture for something projected horizontally. And whenever you do anything in physics, you always have to have your frame of reference. So in this case, the frame of reference is always where motion begins, or the starting point. And you have to be consistent. So if I'm measuring, if there's a ball or a rock on the top of this and I'm measuring from here down, this distance is going to be negative. If I'm measuring from this over, this is going to be positive. Now, the best way to do these problems is you break everything up into X and Y because the motions are independent of one another. So we're going to do everything separately, and even though books don't really do this, this is the easiest way to do it. Now, in your notes, you have this example problem. So what I'm going to do is I'm just going to work this out separately, step by step. So it says a stone is thrown horizontally. So again, we're going to write our given. We're going to write what we want to find. And it's essential to draw a diagram when you're doing projectile motion. Now the difference here is when we write our given, it says that VI is equal to 15. And then it says it was thrown from the top of a cliff 44 meters high. So then it says, how long does it take the stone to reach the bottom of the cliff? So I want to find the time. And then it says, how far from the base of the cliff does the stone strike the ground? Which I'm going to call that X. But let me draw my picture. So here is the cliff. Here's the stone. It's being projected horizontally like this. So this is my initial velocity. Again, this is my frame of reference. And because gravity is the only thing acting on it, remember, once I let go, there's no longer a horizontal force pushing on this, so the only thing pulling it down is the acceleration due to gravity. I need to have my frame of reference, which is actually going to be right here. You know, up and to the right is positive, down and to the left is negative. And I need to be consistent. Now, because I'm measuring and my frame of reference is my starting point, this Y here, this is actually going to be negative, and then when I measure this X here, that's going to be positive. So when they tell me the cliff is 44 meters high in my given, that's actually going to be negative 44. But whenever you do projectile motion, you're always going to separate your values. You're going to have X and Y. So I'm going to have my X, then I'm going to have my Y. Now, all the variables we have, there's never any horizontal acceleration because nothing's pushing on this. So the horizontal acceleration is always going to be 0. I always write that. Now, the way a lot of books do projectile motion is they take our same kinematic equations and they like change them into new ones and say, oh, here's the equations for projectile motion. It's the same equations, but if you always know the horizontal acceleration is 0, you don't have a problem. Now, the vertical motion is G is the acceleration. It's always going to be 9.8 meters per second squared. So in every single problem, you're going to write this no matter what, because that's never, ever, 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 ever going to change. What you're going to do next is you're going to then take, if you're given your initial velocity, you're going to do the horizontal and vertical. So if we look at a section, here's VI. VI is all horizontal. It has no vertical component. So VIX is equal to 15, and VIY is equal to 0. Are we given anything else in the problem? Because if you remember our equations all have 4 variables. Well, I need 3 things to find a fourth. So the last thing was I was given the height, so y is equal to negative 44 meters. So now I know that I'm going to start on this side because I have 3 things here. Now remember, we're using the same equations we used before. Remember our equations like we had x is equal to VIT plus 1/2 AT squared. Now we take the same equation and I can either apply it horizontally, so it becomes x is equal to VIXT plus 1/2 AXT squared. But you know what happens? Since AX is always 0, that disappears. Now in some physics books they're like, oh magic, here's your equation for horizontal displacement for projectile motion. That seems like a lot to memorize. Just remember our same equations and AX is 0. If I apply this vertically, it becomes y is equal to VIYT plus 1/2 GT squared. So I can take any of my equations and I can apply them both horizontally and vertically with various subscripts. Like if I had VF is equal to VI plus AT, this would be VFX is equal to VIX plus AXT. But AX is 0. So now we see that in projectile motion that the final horizontal velocity is equal to the initial horizontal velocity because there's no acceleration, this never changes. And we can use any of the equations. So let's work this problem. Again, where do I start? I look at which side I have 3 things on, and that's how I know where to start. So now what do I have? Well, I have G, I have VIY, I have Y, and I want to find the time. So which equation has these 4 variables? Well, it's the equation that says y is equal to VIYT plus 1/2 GT squared. Now, we're going to make our life simple. VIY is 0, so this whole term goes to 0. So this becomes y is equal to 1/2 GT squared. Now, since I want to solve for t, I'm going to rearrange the equation to solve for the unknown in terms of the known. So first I'll multiply both sides by 2. I'll divide both sides by g. And then I want to get rid of the squared. I'll take the square root of both sides, so that's t. Now I'll substitute in my values. 2 times, be careful with your sign convention, negative 44 divided by negative 9.8. And what you'll notice is that the negative in the numerator cancels with the negative in the denominator, so I don't have a negative under the radical. So this comes out to be 3 seconds. Now it says to find how far it goes, which is x. So for the b part, again, my basic equation horizontally is x is equal to VIXT plus 1/2 AXT squared. AX is always 0, so this disappears, and here's my equation. Now, once I find the time here, the time is the same. So when this goes down, the x time and the y time is the same. So if this time ends up being 3 seconds, the time here is also 3 seconds. Don't forget, time is scalar. Time doesn't have a direction. So now when I want to know how far it goes, x is equal to VIX, which is 15, times the time, which is 3 seconds. So this 15 times 3 is 45. And remember, I always want to check my work, so I'm going to carry my units through and cancel them to check my work. So this cancels with that, and I end up with meters, which is the correct unit for displacement. And this is how I do projectile motion problems for projectiles that are launched initially all horizontally, like in this picture. And again, to recap, you have to draw a picture. After you draw your picture, you're always going to do x and y givens. AX is always 0, g is always negative 9.8. if you're given the initial velocity, you're going to break it up into the horizontal and vertical components. Then you're going to look at your problem and you're going to say, well, what else do I have? And then the same method that we did before, where we write down, well, what do we have? This determines which equation that we're going to use. And that's how we do projectile motion.